Welcome. Here, we break down complex electrical engineering concepts into simple, practical, and engaging explanations. So stay connected with the world of electrical engineering.
Let's learn how a nickel-cadmium battery pocket plate is made. First, we start with a nickel-plated steel strip that has tiny holes. This strip is strong and allows the electrolyte to move through it. Next, the strip is bent into a pocket shape. Inside each pocket, we put the active material. Positive plates get nickel oxyhydroxide. Negative plates get cadmium. Then, the pocket is sealed by pressing its edges. This holds the material safely inside. After that, many pockets are joined together to make a pocket plate. A metal tab is added so the plate can connect to the rest of the battery. Now, positive and negative plates are stacked one after another. A separator is placed between them so they do not touch. This stack is placed inside a plastic battery case. Electrolyte is added and the terminals are fixed on top.
Finally, the nickel-cadmium battery is ready to use. This type of battery is very strong, lasts long, and works well in difficult conditions. Now let's take a simple look at how a nickel-cadmium battery works on the inside. A nickel-cadmium battery has two main electrodes, a positive electrode and a negative electrode. On the positive side, the active material changes between two forms, nickel hydroxide when the battery is discharged and nickel oxyhydroxide when the battery is charged. On the negative side, the material also changes between two states, cadmium hydroxide during discharge and cadmium metal once the battery is fully charged. Let's see what happens during discharge when the battery is powering a device. The reaction moves from left to right. Nickel oxyhydroxide reacts with water and cadmium metal to form two new products, 2NiOOH plus 2H2O plus CD arrow 2NiOH2 plus CdOH2. So during discharge, the positive plate turns into nickel hydroxide. The negative plate becomes cadmium hydroxide. Now, when the battery is plugged in for charging, the entire reaction reverses. Electrical energy pushes the materials back to their original forms. 2 nickel hydroxide plus cadmium hydroxide yields 2 nickel oxyhydroxide plus cadmium plus 2 water. So during charging, nickel hydroxide becomes nickel oxyhydroxide again, and cadmium hydroxide returns to cadmium metal. Because this reaction is fully reversible, nickel-cadmium batteries can be charged and discharged hundreds or even thousands of times. The electrolyte inside the battery is potassium hydroxide, or KOH, mixed with pure water. A small amount of lithium hydroxide is added to improve life and high-temperature performance. The important thing to remember is this: the electrolyte does not take part in the chemical reaction. It simply helps ions move and does not corrode the internal structure. This strong and stable chemistry is the reason nickel-cadmium batteries can operate reliably from extremely cold temperatures, like -40 degrees, all the way up to +70 degrees Celsius. So, in simple words, nickel-cadmium batteries work because nickel and cadmium keep switching between different chemical forms during charge and discharge, and they do it again and again with excellent reliability. Let us compare three major battery technologies: nickel-cadmium, lithium-ion, and lead-acid. This radar chart highlights how each technology performs across key parameters that matter in practical applications. First, look at energy density. Lithium-ion clearly leads here. It stores more energy in a smaller and lighter package. Nickel-cadmium comes next, while lead-acid sits at the bottom. Next is power density. Again, lithium-ion performs best, delivering high current quickly when needed. Now move to extreme temperature performance. This is where nickel-cadmium stands out. It performs reliably in both very low and very high temperatures. Lithium-ion is moderate,
while lead acid performs the worst under extreme conditions. The cycle life comparison also favors nickel-cadmium. Nickel-cadmium batteries have one of the longest operational lifespans. Lithium-ion offers decent life, and lead acid has the shortest cycle life of the three. When it comes to cost, the chart shows nickel-cadmium as the most economical option in terms of acquisition or long-term ownership. Lead acid follows, while lithium-ion remains the most expensive technology. Looking at safety, nickel-cadmium scores the highest, followed by lead acid. Lithium-ion ranks lower due to its sensitivity to thermal runaway and charging conditions. Finally, consider maintenance. Lithium-ion requires almost no maintenance. Nickel-cadmium needs moderate attention, while lead-acid batteries demand the highest level of regular care. Overall, nickel-cadmium technology offers strong reliability, excellent safety, outstanding temperature tolerance, and low capital cost. Lithium-ion excels in energy and power density with minimal maintenance. Lead-acid remains a low-cost option, but with clear performance compromises. This comparison helps you choose the right battery technology based on your application needs.
Thanks for watching. We hope this video helped you understand electrical engineering concepts better. If you enjoyed the content, don't forget to like, share, and leave your thoughts in the comments. Stay with us and stay updated with more videos on transmission lines, substations, and power systems. Until next time, stay curious, keep learning, and keep the power flowing.